Today we're going to take a look at section 7.1, which is going to begin our discussion of decimals in chapter 7. And as we start with this section, the first thing I want to take a look at with you is what it means, or what the phrase or word decimal actually means. Decimal comes from the Latin word meaning 10. So when we talk about us having a base 10 system, that's why that use of that word decimal, okay? Deci meaning 10. And the language that we're using when we're talking about or decimals, has to do with the place value. So I want to talk a little bit about place value first. So let's start to the left of the decimal, and we'll start with this place right here. What is this place called in the decimal system? This is the tens place. This one has a couple of names in the decimal system. What do you remember? Ones. Anybody else remember anything different? Sometimes you'll hear it called the units place. When we read one of these decimal expansion forms, what do we read this decimal saying? Do you remember? We say "and" when we cross the decimal place. I specifically remember in second grade being in trouble in class because I said that this number, and I would do it all the time, was the number 527. And it's not "and" because there's no decimal. Whatever. But that is the language that we use properly. We don't use the word "and" unless we see that decimal place. So, all right, so now we're actually moving beyond the decimal. What is this place called? That is the tenths place. And make sure when you're using that language that you pronounce it very clearly so that you hear that TH on the end. Because it would mean something different, right, if I said tens instead of tenths. What comes after the tenths place? That is the hundredths place. What's the next one? That is the thousandth place. What's after thousandths? Close. First we'll have 10 thousandths. After 10 thousandths we have the 100 thousandths. And I don't have space more for it. Well, I guess I could put it right here. We'll do more of them just for fun. What would come after the 100 thousandths? That is millionths. And we could keep going if we needed, right? We'd have 10 millionths and 100 millionths and so forth, right? Everybody good with that? Okay. So as we're taking a look at that, the first thing we want to be able to do is we want to be able to take this number and we want to say it appropriately. Because if I asked you to say that number, I bet we could all say in unison what we would say. We would say 32.4236. Wait. And some people wouldn't even say point, they might even say dot these day and age. So we're going to say it properly. How would we first say? The first part's the same. 32 actually is said as 32. There is a hyphen between the 30 and the 2. And then we say the word "and." Now the next piece of this is actually saying the 4236 as though it were the number 4236. All right, so that would be the number 4,000. I didn't mean an S there. 4,000. What's next? 200. 36, again there's a hyphen between the 30 and the 6. And after I actually write all that out, I indicate the place value in which I ended. That's where this 6 is right here. What place value is that? Is it 10,000? Excellent. All right. So then we would write at the very end of this 10, and there's a hyphen again, thousands. Okay, so this is 32 and 4,236 10 thousandths. That's how we would read that. All right. We're going to go the other direction now as well. We're going to take the language and we're going to rewrite that as a numeral. So in our wonderful notation, we get to look first for the "and." for our decimal point. So what's going to come before that? Right, 536, right, 536. And what's going to come after that? So be careful. Is it? I've heard two things. I've heard some people say 076, and I've heard some people just say 76. Which one is it? Why is it 076? Right. That last number, the 6 in this case, needs to be in the thousandths place in order for this to match up. Is that okay with everybody? All right. All right, so in Math 1, we talk about whole numbers, and then we get into these other rational numbers, fractions, and decimals, and so forth in Math 2. And in Math 1, we actually explore this idea of base 10 for the first time. We're going to explore the other half of base 10 in this perspective. So I want you to write that same 5 values to the right. I know I added a 6th value when we were working on it, but 5's enough. So in base 10, we actually talk about this being the ones place and the tens place. And the next place is called the hundreds place and the thousands place. And we have numbers that we write for that, right? So we used the word tenths right here to the right of the decimal. And tenths is the number 1/10. That is 1/10. The next place value is the number 1/100. And then we have the number 1/1000, 1/10,000, and the number 1/100,000. Now, there's another way to write these numbers on the right. So what I'm about to write in red, you don't need to know this, except to the extent that if you look in the back of the book, they're going to do this for you. I am perfectly comfortable and actually prefer that you leave it the way that I just wrote it. Okay? But what they're going to do in the back of the book is instead of writing 1/10, they're going to write this as 10 to the negative 1. They're going to write this as 10 to the negative 2, and so forth. And while that is absolutely correct, and in certain math classes that is what I would prefer, I don't prefer it here. And the reason I don't is because I think you've lost the intuitiveness of what in the world those values mean once you make them negative exponents. All of a sudden you've made it to a level of abstraction that you've lost the connection with as well. I would much rather you connect the idea that a certain location in the decimal expansion relates to a fraction than it relates to a 10 with a power that's a negative exponent. Are you guys with me on that? So let me do the next part, example 3, with you. And then I'll show you what the back of the book is actually going to say when you look at it, if you saw this one on number 3. Okay? So the first thing we're going to do is we're going to take each value, and we're going to write them, and right next to them we're going to write the power or the base place the value that it's in. So that number 1 is in the what place? That is the hundreds place. So we're going to write 1 times 100. I'm going to encourage you to write the zeros just so that you get in the habit of seeing all the pieces there and it doesn't look like there's anything missing. Where's that first 0 in? That's the tens place. The 3 is in the ones place. The next 0 is in the tenths place. And the last 3 is in the 100th place, right? So if you were looking in the back of the book, they're going to do this. They may even leave the zeros out, I'm not sure. But they're definitely going to write that as 10 squared. They're going to write this as 10 to the first. They're even going to write the number 3 times 10 to the 0, because that's actually a power of 0. Can give me back a 1. They're going to write this one as 10 to the negative 1, and this one is 10 to the negative 2. So that's what you're going to see in the back of the book, but I would prefer that you leave it like this. Okay, and that's what this note here at the bottom is referencing, what your book's going to do. This notation is actually really good, especially if we're dealing with only 2 decimal places, at thinking about something very concrete that you use every day. Any thoughts? Money. It's really good for money. So if you had this number, 103.03, right, this number, this is actually one $100 bill, right? You've got 0 tens. You have 3 ones. You have 0. What does this 1/10 represent? dimes, you'd have 0 dimes, and then here you'd have 3 pennies. Now, I know that in our money system we have other coins that don't exactly correspond, but we could get by with those coins and dollar bills only, and it would work. I just don't know that I want to carry 9 $1 bills, right? Or 9 pennies and things like that. So we have other coins, but this would still work. All right, so one of the things that we can do is we can actually draw what's called a decimal square grid. This is sort of the visual imagery of what's going on. And in a decimal square grid, we're going to see if I can find out where this is again. I think they've done an update since I've been in here because I don't see the notes, my notes matching any longer. Where to find these guys. All right, forget it. All right, we'll just draw it. All right, so we're going to draw, not that. Let's try to do right again. Clicked on the wrong thing while it was moving. All right. We're going to draw a rectangle, or actually it's going to be a square, but it looks rectangular when this actually does it. And we're going to split it into 10 columns and 10 rows. Do your best to make them look reasonable. I will do my best as well. No promises. Do that. All right. Let's try one more time. Okay, do I have 10 of them now? I think so. My daughter was making a window on a picture the other day like this, and my husband was saying, "Oh, look, prison bars." Okay, so they should all be exactly the same size boxes, and obviously they're not, but you've got the picture in mind, right? All right, so this is via decimal square grid. It's got 100 little boxes, and each of those boxes is 1/100th, okay? And so when we draw the grid, if we're wanting to shade in a number, 2300ths, what would we do? We would shade in 23 boxes. And so I know that some of you are really funny, but just pretend with me for a moment. Would it not make the most sense to shade in 2 full rows and then 3 more boxes? You're not going to make me very happy if you shade in 23 random boxes. Okay? Please don't do that. So we got 2 full rows and 3 extra boxes. And this is the decimal square grid picture visual for the number 2300ths. All right, let's take a look at the theorem. Any rational number, a over b, in simplest form, can be written as a terminating decimal if and only if the prime factorization of the denominator contains only 2's and 5's. This is actually giving you information about how in the world you know whether a fraction turns into a decimal but terminates. Terminates just means stops, okay? And it doesn't sort of like do the repeating thing. How do we know when that happens? And so this is telling us that we know that when that happens by first reducing the top and the bottom, if they can be reduced. That's really important. That's what people usually forget, is that reducing at the top and bottom. You've got to reduce first, okay? I've got terrible examples up here because neither of them need to be reduced. Sorry. But you've got to remember to do the reducing step, okay? If it reduces, you've got to reduce first. Once it's reduced, then you just look at how the denominator factors. So, number A, or letter A, 3 over 8, is reduced, right? 3 and 8 don't have anything in common. So what we do is we take the value 8 and we factor it. How does 8 factor? Let me do it this way. Some of you haven't had that from me, so. How does 8 factor? 2 and 4. And can we go any further? Yep, the 4 goes into 2 and 2. So the 8 factors into 2 times 2 times 2. Is this factorization such that it only contains 2's and 5's? Yes. It doesn't have to have, it says that we have to contain only 2's and 5's. Now, it doesn't have to have both. It just can't have anything else. Did you guys hear that? It doesn't have to have 2's and 5's. I know that word and is there, but it's sort of an and or condition. It can have either one. This value, we actually know what it is. You've seen it before. We're going to work it out here in a second. But it does work. It's a terminating decimal. So this one terminates. This one terminates because the denominator contains, in this case, it's actually only 2's. That says only 2 at the end. Okay, so let's do part B. I've got 5 over 12. First of all, we want to make sure, is it reduced? Is there any ability to reduce the 5 and the 12? And there's not. So, what do we do next? Factor the 12. So how will the 12 factor? 2 and 6, okay. And then the 6 factors into 2 and 3. So the number 12 becomes 2 times 2 times 3. So will this terminate? No. This one does not terminate. And it does not terminate because of the 3. In the factorization of the denominator.
So is it just a rule that it has to contain a 2 or a 5?
It doesn't have to contain a 2 or a 5. It can only contain a 2 or a 5.
So if it, like if once you factor it out, I don't know what number it would be, but if it was like 2 times 2 times 5,
Yes.
that would work.
Absolutely. So it can contain 2's, it can contain 5's, or it can contain a combination of 2 and 5's. But if it contains anything else after it's been reduced, then it will not be able to actually be terminating. What we would have when we have that situation, like this one right here, is what we call a repeating decimal. It's actually going to have a repeating point something in there. And we're going to actually encounter that in section 7.3, which is actually next Thursday. So we will see what happens to this one later, but it's not terminating. Okay. Then the other part, before you turn, the other part of the directions actually say mentally determine if it represents 1. Then it says write it as a terminating decimal if so. So we only have to write one of them as a terminating decimal, right? Only one that terminates, the 3 out of 8. So do you guys remember how you change fractions into decimals? Your calculator will do it, that's true. You're not going to do it with your calculator, although you can do it to check it with your calculator. If you're going to do it by hand, how do you do it? You use the division, right? I mean, that's what this bar actually means is division. So you divide the 3, which is the top, by the bottom, which is 8. So this one right here, move it over just a little bit. 3 goes into 8. Well, that doesn't work, right? 8 goes into 3. So we're going to put a decimal place 0 here. The decimal comes up, but we treat the number 3 as the number 30 now. So we ask ourselves, how many times does 8 go into 30? That will be 3. What is 3 times 8? 24. And we subtract, right? So what's 30 minus 24? 6. All right. Move that down. And then I have, this is dumb, why I'm doing this. I'll just do it down here. All right. 6, right? All right, then I would do the same thing. I would add another 0 here and bring it down. So how many times will 8 go into 60? It's 7. Very good. 7 times 8 is 56. Brushing up on those multiplication tables might be part of your weekend plan. I'm not sure. Sorry, I said 56 and then I wrote 57. Let's try again. 56. And then we subtract and we get 4. We add another 0 or tack another 0 on there. How many times will 8 go into 40? 5. And 8 times 5 is 40. And we're done. How do we know we're done? We got a remainder 0. We actually finished the process. And so there will come a point when you get 0 as a remainder if it's terminating. So if you keep going and going and going, you might want to go back and check and make sure you didn't just already forget to check the terminating status. Okay? So it should stop if it really is terminating. All right, the next thing we're going to take a look at here is comparing and ordering decimals. So as we compare and order decimals, we can do this by lining up the numbers by place value. We read from left to right to find the first place where they are different from one another. And then we compare the different digits. So as we're taking a look at this one, they all have a 13 in them, 13 and then a decimal point, right? So we're going to line them up vertically with the decimal point as the location that they need to match with. So this is 13.492, 13, the decimal point, 4918, and this one's actually longer, 3, and then 13, the decimal point, and 49199. They actually have a lot of decimals, a lot of the value in common. Where's the first place where they are different? Reading from left to right. The thousandths place, right here, yeah? In the thousandths place, most of them are still alike. One of them is different. The one that is different, is it larger or smaller than the other ones? Larger. So this one is my greatest. So if I'm writing this from least to greatest, this is actually going to be the 4th number in my list, right? Because it's the greatest number. All right, so after that location, we'll keep moving to the right. We don't need to look at problem number 2 or number 2 anymore, or whatever, because we already talked about him. So now we're looking at the 9 at the top, the 8 as the 3rd number, and the 9 at the bottom. Which one is different? The 8. And is the 8 smaller or larger than the rest? Smaller. So this is actually my smallest or my least. So when I'm listing it, it's going to be the one that I list first because I'm supposed to be doing it from least to greatest. And then the last thing I have to do is I have to look at the last, I'm looking on the first and the last numbers now because they're the only ones I have left to look at. And when I do this particular number and I compare them, there's a 9 in the last one, but there isn't anything in the first one. So what's there? There's a 0. So we'll just go back and put a 0 there, right? So that we can compare them. And then what does that tell me? The last one's the 9. How does that one rank? Is it 1st, 2nd, 3rd, 4th? What is it? This one would be the 3rd in the line because it's larger. The 9's larger than the 0. So this one would be the 2nd smallest, actually. 2nd smallest. And this would be 2. So when we're rewriting these, we actually have to write them in order. I'm going to use less than signs just to indicate that I'm really being careful on the order being correct. That is the smallest one being first. So the least one is actually the 3rd one that's listed. This is 13.49183. You can put a comma or you can put a less than sign. What's next? The top one, right? So 13.4919. And then I have the last one, 13.49199. And then I have the second one, which was 13.492. It's all good? Okay. One last problem. What is the meaning of the word tithe? Where have you heard it? Church. You guys heard it at church. It actually it isn't directly related to money, although we use it in the church to relate to money, right? That's where we see it in relation to. What does tithe mean? 1/10. That's exactly right. So if you look at this, I know that this is not the most accurate source of everything possible, but from Wikipedia, this means 1/10 part of something. So you've heard it, Hannah mentioned in reference to money. That's where we use it mostly when we talk about it in relation to church, right? 1/10 of your income that you put your tithe in the offering plate. Sometimes you'll hear people refer to tithing their time. You ever heard that phrase before? Talking about giving 1/10 of their time in some kind of a manner, or 1/10 of some other kind of a resource that they have. It doesn't have to be money. And so that's why you see money actually not mentioned in this. That's just where we use it the most. So 1/10, I wanted to show you a little bit about this because I think it's interesting. 1/10 means this, right? 1/10, 1 out of 10. Or we equivalently use the decimal expansion 0.1. And in practice, finding 1/10 of, let's say, $50 means we do what? What do we do? What do you really do? You move the decimal. How? We move the decimal to the left one place. In this case, it would be $5. And the reason we do that is because moving the decimal to the left is the equivalent of dividing by 10. Right? When we move that decimal, it's the equivalent of dividing by 10 because we have a base 10 system. Decimal. That's why that happens. All right, so jot these numbers down because I know that not all of you guys have this showing up when you print that out, so make sure you have those written down.